Hello students, today we are going to start a new chapter. So this is chapter 9. So we have already completed chapter 8 and I request you to solve the example problems given in chapter 7 and 8. So chapter 9 is about 2D elasticity. So in chapter 7 we looked at mainly the scalar field problem, meaning that only one variable per node, but now we will be looking at 2D elasticity. There will be two variables per node, meaning that displacement in x direction and displacement in y direction. So okay, so problem is now 2D elasticity. Elasticity. Okay, so problem would be something like this. So there will be some domain omega, some portion will be fixed, yeah, and some portion will have some forces given like this one. Okay, so all these will be on the boundary. So there will be gamma naught, for example, where essential boundary conditions will be prescribed, meaning that some displacement will be prescribed, and there will be some another gamma where the forces or traction will be prescribed. Okay, and this is a whole domain where there may be some body forces given. So body forces, as we saw in 1D problem, so there was a body force which was actually force per unit length. In this case, this will be force per unit area in that case, and B is a vector in this case. Okay, so at every point the forces may be in different direction. So hence this is B. So this problem if you want to solve, then how to solve it? Well, first thing we need to know the strong form, right? A strong form. So what is strong form? Meaning that what is the differential equation that we have to solve? Okay, in order to derive that, we have to take a small element or a small portion, infinitesimal portion, a square portion of the original domain. Let's draw it here, which will be like this one, and then let us say the length of this is dx, height of this infinitesimal, the area, test area is height is dy, like this, and we know that there is a force B per unit area. So this is given here. Thickness we can assume to be as 1. So let's say thickness of this plate to the domain is 1 unity, we can assume. So let's see the forces that will be there. So in elasticity problem we are dealing with the forces, or there will be a stress. So let's call it sigma xx and sigma xx in both the direction, but there will be maybe some variation when you go from here to here. So let's say here it is sigma xx, this here it is d sigma xx dx times dx. This is the whole total sigma here. Similarly, here it will be sigma y, and here this will be sigma y plus del sigma y over sigma yy. Let's call it sigma yy. So sigma yy plus del sigma yy del y times dy. So these are the normal stresses which will be there. Now apart from the normal stresses, there will be also the shear stresses. So then we have tau xy, and so we know that from solid mechanics that all these tau will be the same. However, there will be variation because of the little variation because of the forces. So the forces, what I mean is when you go from one point to the other point, then the stresses may vary. However, at one point, the all these tau, the shear forces here, means these two shear forces will be equal if you are looking at one point. However, if you take a very small element like this one, infinitesimal area, then there may be variation. So from tau xy here, this, if you move by dx distance, here it could be tau xy plus del tau xy del x and dx. Okay. Similarly here also, if this is tau xy, this one will be, so I will write here, so this one will be tau xy plus del tau xy over del y dy. Okay, so we have these stresses here. The next thing will be to find the equation of equilibrium. Okay, so we will apply the Newton's second law of motion. So here B will also be there, the body force will also be there. So if you apply the equation, the equilibrium here, so there will be two directions in which we have to apply the equilibrium. So in x direction first, in x direction, so there will be, this is sigma x, so this sigma, this direction minus this one, so we have sigma xx plus del sigma xx over del x dx, this minus this one, so minus sigma xx, so this becomes 1. Then if you see, this is also in x direction, tau xy here, so we write plus tau xy plus del tau xy del y, this one, so this one, so this is tau xy plus del tau xy over del y times dy minus this, so tau xy. So in x direction we have this one, sigma x plus this minus sigma x, then plus we have this one, tau xy plus del tau xy over del y times dy minus tau xy. So we have these stresses, and then we have this. So again, one thing we forgot here, so we also have to apply the area in order to find the right forces here. So equilibrium is always for the forces, not for the stress. So we have to actually write the multiply them by area. So area for this, for all these, the area will be this one, which is what, dy times 1 is the thickness, so dy. So we write dy here, dy, and here also dy we wrote here. Here this will be, so this area now, because we are talking about this one which is tau xy, so this is nothing this is dx, so we write dx here, and this is also dx. Okay, now b, so let's say b has two parts, so one will be, so let's say just we write here b is equal to two things, bx in I direction and by in z direction. Yeah, so in that case what we get here is we have to write plus bx, that's a body force in x direction, multiplied by total volume. So body force is the force per unit volume. However, here this is 2D problem. So since the thickness is unity, so body force here turns out to be force per, you can also write it in terms of force per unit area. So bx multiplied by dx times dy times 1 basically. Yeah. So this is a total force, okay, acting on this infinitesimal element in x direction. So this becomes equal to 0. So what we get here is if you work out here sigma xx multiplied by dy, sigma xx multiplied by dy, so it will cancel out. Similarly here tau xy times dx and tau xy dx, this one will cancel out, and what we have finally will be sigma dxx del x, then dx dy plus del tau xy del y dx dy plus bx dx dy equal to 0. Or we can write that sigma del xx over del x plus del tau xy over del y plus bx equal to 0. So this is the equation of equilibrium in x direction. Similarly, similar analysis we can do in the y direction, and we will get sigma del sigma y over del y plus del tau xy over del x plus by equal to 0. So instead of deriving like this one, we will just write this equation. So rewriting the equation of equilibrium in x direction first. So we have del sigma xx over del x plus del tau xy over del y plus bx equal to 0, and similarly we will get del sigma yy over del y plus del tau xy over del x plus by equal to 0. Yeah. Or in equation the matrix form also we can write, and how will we write? There will be some operator matrix here, and here we will have sigma xx, sigma yy and tau xy, and plus we will have bx term here, by term here, and that will be equal to 0 basically. Yeah. Or since there are two terms here, we can also write it as a 1/2 vector with 0 entries. So here this will be in this case del over del x, which will operate here. So we get the first one, second term will be 0, second term is 0, and third term is del over del y. So this is the first one. Second term, the second equation will be here, this is 0, and then we have del over del y, and then we have del over del x. So this system of equation we can also write in this term, in this form, like this one. Okay. Or in this we also can write as del s. Okay, del s, say, and this the whole term we can write as sigma vector plus this we can write as a v vector, and they equal to 0 as a this vector. So this can also be written something like this one. So here it is, we are writing vector term, this one, this also as some this is operator which is similar to the divergence of a vector. So actually instead of calling this as del s, we can also say del ts rather, so that this becomes of exactly the same form of a divergence. When we write divergence in matrix form, we write as delta of transpose. So does y we can also write like this one, where delta s is a operator and which will look like the transpose of that. So del over del x 0, 0, del over del y, and here del over del y and del over del x. So like this one, and this is just write where, and this is sigma vector which is equal to sigma xx, sigma yy, tau xy, and b vector given by bx and by. So we can write like this one. So what is the conclusion? This is the what the equation of equilibrium is, or the a strong form. Yeah, so this is the a strong form. However, we still have to elaborate. So this is a strong form. However, we still have to find out what is sigma is, how sigma is related to the nodal variable, and nodal variable here is displacement. So we have to first relate sigma with epsilon, that is material property. We have to find out the constitutive relationship, and then we have to see how a strain is related to the displacement, as we have been doing in all cases. In 1D problem also, we first found out how the equation of equilibrium is, then we related sigma, that is stress with a strain, and then we related a strain with displacement. That is what we will do. So next will be to how sigma and epsilon are related. For that, again, how you write sigma xx in terms of epsilon yy. So there are two things. So we have sigma. Now we are talking about at the same point. So although we are drawing like this one, but it means at the same point we have sigma xx and then sigma yy here, and then we have tau xy, tau xy, tau xy, tau xy, like this. Yeah, and the corresponding strain, this is what we drew is stress. The corresponding strain will be epsilon xx, epsilon yy, and then we will have gamma xy. So the gamma xy are the strains, the shear strains. So gamma xy, gamma xy. So epsilon xx, epsilon yy are normal strains. Gamma xy is the shear strain. How are sigmas and epsilons are related? So remember, we are talking about a 2D case only. So we are not talking about sigma zz and anything that has a z component in that. So sigma zz or gamma or tau xz or tau yz are similarly strains which has a component in z direction that we are not talking about now. So here it's easier to write strains as a function of stress. So for example, epsilon xx normal strain in x direction will be because of both the stresses sigma xx and sigma yy. All this what we are doing here is in the solid mechanics course that you have already done during your BTech. So epsilon xx will have first component because of sigma xx. So we can directly write sigma xx over E. Again, this derivation we are doing for a isotropic case. So after this epsilon xx will also be because of the sigma yy, okay, and the relationship will have a Poisson's ratio there. So if sigma y is this direction, so the strain caused by sigma yy will be sigma yy over E, and then times nu, which is the Poisson's ratio, and negative direction will add here. So that means there will be a component minus nu, then sigma yy over E. All this derivation is for isotropic material, as I said earlier. So this is the equation, how sigma epsilon x is related to sigma xx and sigma yy. Then similarly in y direction we will have here we will have minus nu sigma xx over E plus sigma yy over E, or another this is gamma xy will be equal to tau xy over G, where G is the shear modulus. So we can also write here as epsilon xx yy and gamma xy is equal to this. We can also elaborate further. So G is equal to E over 2 times 1 plus nu, which is for the isotropic case. So we can write here this will be G equal to 2 1 plus nu over E and then tau xy. Okay, so that we don't have to write it in terms of G, which can be determined from E and nu. Okay, again all these things you have already studied in solid mechanics or strength of material class. So we are just repeating it here. So we can write here is here. So we have 1 over E, then minus nu over E, then 0, then minus nu over E, 1 over E, 0, and 0 0, and then we have 2 1 plus nu over E. So this is one matrix and multiplied by sigma xx, then sigma yy, and then tau xy. Okay, so okay, so also you write it as a strain, which is a vector, is equal to d. We will not call it d, let's rather call it d inverse. So this is d inverse and then sigma vector, so that we have sigma is equal to d, okay, which is a matrix, and this one where d will be inverse of that. So we have to find out what the d is. So d is equal to 1 over e minus nu over e 0, then minus nu over e 1 over e 0, then 0 0, and here 2 1 plus nu over e. So this is the what d is. No, this is inverse of that. Yeah, so d will be this matrix to the power minus 1, indicating that the inverse of this matrix. So d is the inverse of what? Of 1 over e minus nu over e 0, 1 minus nu over e 1 over e 0, and 0 0, and you have 2 1 over nu over e, so inverse of that. So we can easily find out the inverse of this matrix. So will be equal to, so if we take out 1 over e from here, so we get equal to 1 over e inverse of that. Okay, and then we have 1 minus nu 0 minus nu 1 0 0 0 2 1 plus nu inverse of that. So that is equal to 1 over, that is simply e multiplied by, we just invert this one and this will be simply 1 over that. So okay, so just if you want to invert this one only, so if you see here, we can also invert this first, and we know invert of the inverse of this will be 1 over 2 times 1 plus nu, that we know already. So since this one, the component of this is 0 0 here, so we can inverse them independently. What I mean is, let's first find out 1 minus nu 1 inverse of that, so which will be equal to 1 over 1 minus nu square multiplied by here 1 1, here nu and nu, like this one. So what we get here is simply like this, will be 1 over 1 minus nu square, nu over 1 minus nu square, nu over 1 minus nu square, and 1 over 1 minus nu square is the inverse of that. Yeah, so d we can write as d equal to, now this you can put it directly here, so we get e multiplied by and we get 1 over 1 minus nu square, nu over 1 minus nu square 0, nu over 1 minus nu square 1 minus 1 minus nu square 0, and 0 0, and then inverse of that, so becomes 1 over 2 1 plus nu. So this is what the inverse of that is. Yeah, so if we take out 1 minus nu square outside, so d becomes equal to e over 1 minus nu square, and then we will have 1, then nu 0, then nu 0, nu 1, so 1 nu 1 0, then 0 0, and 1 minus nu square divided by 2 1 plus nu. So like this, yeah. So or d is equal to E over 1 minus nu square and 1 nu 0 nu 1 0 0 0, and we have 1 minus nu over 2, like this. Okay. Remember, this is for plane stress. So plane stress problem. Okay. So here we assumed that this is plane stress, so it's a thin member, meaning there may be a strain in z direction, but there is no stress in z direction. So plane stress problem, sigma z is equal to 0. So this is what we have assumed in this case. Okay. Similar derivation can be done for plane strain problem. So so we will write this is plane stress problem. So plane strain problem, so in this case epsilon z is equal to 0. So for that also you can derive accordingly. The bottom line is that we have a relationship between sigma and a strain, and the case what we have used is plane stress case, and we have the final relationship, and the relationship is sigma xx sigma yy tau xy is equal to we have E over 1 minus nu square, and then we have 1 nu 0 nu 1 0 0 0 1 minus nu over 2 multiplied by epsilon xx epsilon yy and gamma xy. This is the stress-strain relationship or constitutive model or the material properties. So this is actually a material property or generalized Hooke's law. So the first equation we found out of equation of equilibrium, that was actually relationship between the stresses. Second equation we found out is the stress-strain relationship, and now we have to find out a strain displacement relationship, otherwise we will not be able to get the strong form in terms of the displacements. So how is a strain related to a stress, that we have to find out now. So we will write it one by one. So first epsilon xx, which is nothing but del u x over del x. So where ux is the displacement in y direction. So total u, you can write is that uxi plus uyj, because displacement is a vector, it will have two components, one in x direction, the other in y direction. That's why we wrote like that. Okay. Now epsilon yy is del uy over del y, and gamma xy is given by del ux del y plus del uy over del x. Again, all these equations are from strength of material class. Okay, so we are just repeating it here. So we can also write like this: epsilon xx, epsilon yy, and gamma xy is equal to, there is some operator here, and then we will have two things, ux and uy, like this. Okay, so which operator we have? So let us see. So first this will have del x like this, and there will be 0 here, then there will be 0 del over del y, and then we will have del over del y and del over del x, like this one. Okay, so you may recognize this is nothing but the delta s that we wrote earlier. So this is E as a vector is equal to, we have delta s, okay, and then we have ux, so u as a vector. So this is the strain displacement relationship. Now what we have to do is we have to combine the three equations. Which all three equations? One was the equilibrium equation that relates all the stresses. Second is the material property, that is the stress strain relationship, and third is strain displacement relationship. If we combine them, we will get the equation, the differential equation, or the final weak form. Let's write them here. So we have the equilibrium equation. So delta st sigma plus b equal to 0. This is equation of equilibrium, and then we had sigma equal to d epsilon, and here epsilon is, so this is the one which relates all the sigmas with the force. This is the relationship between stress and strain, and this is strain relationship with the displacement. So all these combined are the strong form. Remember that this strong form is not complete without the boundary conditions. So we also have to write a boundary conditions. And as I said earlier, boundary conditions will be essential boundary conditions and natural boundary condition. So there may be essential boundary condition where gamma u, where displacement is prescribed, and there will be gamma t, where traction is prescribed, meaning the boundary forces are prescribed. Okay, so this may be given by u at gamma equal to gamma u may be prescribed as u naught, okay, which will be function of xy. So which will be function of xy, okay, and traction. So let's just write t here for traction. T gamma equal to gamma t equal to t naught here, and x again this is maybe the function of xy. Okay, so we will understand the meaning of traction now. Traction is same as stress in the sense that both are force per unit area. However, traction is defined on a free surface, and traction is a resultant of both normal and shear stresses. What I mean to say is, let us say we are talking about a structure like this one. So let's say it's a fixed here, and there may be a force applied here. So force is something like this one is being applied here. So if you look at here like this is what it means is this is resultant of both normal stress and shear stress. So what I mean to say is, if we let's consider this very small element here. So this will be something like this. So like this, and we have the traction T. Let us say this is what the traction is. Okay, so this is T like this one. So now what is this resultant, right? That really means that this will have the two kind of stresses. So one is sigma n, and let us say we call it tau n, and this T resultant of both sigma n and tau n both. Okay, so just to make it look right, let's draw the tau not horizontal but at some angle like this one, and also we have to distinguish with the normal vector, which is in something like this one, and tau is the T is like this. So this is T, which is like this. N is normal to this surface. Is a is this vector n, and how it related to sigma x and sigma y. So let's this is sigma x, sigma xx, this will be sigma yy, and then this is tau xy, here also tau xy. Okay, now how is this T, this traction related to sigma xx and sigma yy or tau xy? That we can derive basically from here. Okay, this if this is a traction which is applied, meaning that the stress in a certain direction, a force per unit area in certain direction, and this will be resultant of both normal stress sigma n and shear stress tau n on that surface. Okay, so let us say the length from here to here is d gamma. Okay, and from here to here is dx, and here to the height of that wedge is dy. Okay, now given n we can also write as n equal to nxi plus nyj. Okay, and n is a unit vector perpendicular to the surface here. Okay, now we can find out dx in terms of so dx we can write in terms of d gamma, right? So sorry, the dx will be ny times d gamma, and accordingly dy will be nx and d gamma. Why? We know that if this is vertical, then nx will be 1 and ny equal to 0. N gamma becomes dy, and hence the d gamma multiplied by nx should be dy, and dx multiplied by ny should be d gamma. So, write dx equal to ny d gamma, and dy will be equal to nx d gamma. Okay. So, this relationship we have. Next we have to do the equation, the equilibrium of these forces. So, all the forces in x direction has to equal to 0, and what we find in this case is this is t. So, we write t in x direction. So, tx. So basically just write t equal to txi plus tyj like this. So, tx. So, tx multiplied by tx multiplied by d gamma. Okay. So, tx multiplied this gamma has to be equal, this is all in x direction now, minus d sigma xx times dy, okay, minus tau xy dx, okay. All of these have to equal to 0 like this, okay, or we get tx d gamma minus sigma x and dy is nothing but nx d gamma minus tau xy, and dx here is nothing but ny d gamma equal to 0, or tx is equal to nothing but sigma xx nx plus tau xy ny. So, we get like this. Okay. Similarly, we can find out ty is equal to sigma yy ny plus tau xy nx. This you will find out by equating all the forces in y direction to be equal to 0. So, we have the x component of traction in terms of sigma x and the unit vector perpendicular to the surface, and here y component of the traction in terms of sigma yy and tau xy, and the x and y component of the unit vector perpendicular to the surface on which the traction is being applied. Tx and ty, you can also write it as Tx is equal to sigma xxi plus tau xy j, okay, dot nxi plus ny j. So, this is a new vector which comprises of sigma xx and tau xy, and similarly ty you can write it as sigma yy rather tau xy I plus sigma yy j dot nxi plus ny j. So, this relationship also is important, and we are most likely to use them when we are converting from the strong form to the weak form.